This is the video for Chapter 8, Lesson 3, Estimating a Population Mean. So our guiding question I'd like you to think about is which condition is different for forming a confidence interval for sample means than was for sample proportions and why. So think about the random, normal, independent. Which one of those is different for population means and why? And how does that vary with sample size, which we'll go into. So let's take a look and keep in mind that confidence interval, we're talking about the same thing here. It's just not a proportion. Instead, it's a mean. It's an average. It's not just a number between 0 and 1 like a proportion was. So parts of a whole are a proportion. That's what we talked about before, but the same idea is the same. So we're still talking about trying to estimate the mean here, the true parameter, which would be represented by the center of our normal curve, and different confidence levels. So it's the same idea except for now it's for a sample mean. And because it's a mean instead of a proportion, that changes the standard deviation equation, which we've gone over, and that will give us a difference. So if we sample in a 95% interval, we still have the same idea that we would expect in the long run 95% of ours to be of our intervals to capture the true parameter, which is mu here. Now, sometimes by chance, we're less likely to get a sample mean that's way over here, that's way to the left. That means we had a lot of values that were actually below the mean. The bigger sample size we get, the less likely that is to happen. However, it'll still happen. So our confidence interval means the percent of times in the long run that our interval would capture the true mean. Sometimes when you get your mean down here, these red lines represent intervals that didn't capture it. Now notice that I don't think any of them in here capture the actual mean. The point estimate is this little dot in the middle. None of them are right on. These two here are very close, but they're still not right on the parameter. And we don't need something that's right on the parameter, but they give us a good estimate, and the interval should capture the mean. That's our goal here. Now, same thing applies where 80% confidence interval would have the smallest interval, meaning the lower to the upper bound is the smallest distance, but that means we also, when we have a worse point estimate, we don't capture the true mean in our interval. As we get bigger, the confidence level increases, the size of our interval increases, and then we capture the true mean more often in the long run. So as we go to 95, we capture it more, and at 99 here, we only have this one interval that didn't capture it. So same things in mind here, that we're trying to form a confidence interval that captures the population mean. Now the big difference here is that with population proportions, we could determine the standard deviation based on the proportion. And we had the square root of the quantity p hat times 1 minus p hat over n, sample size. So we could determine the standard deviation. In most of the time, with a population mean, we can't determine it because it's based on the population standard deviation, which we don't know. So we can use a z-score if we're given the population standard deviation. We don't know that. If we don't know that, we use what we call a t-statistic, which we're about to go into. We're going to be mainly using a t-statistic. I'm just showing you the z statistic so you get a sense of how it's linked to proportions. So if we know the population standard deviation, we can use a z-score. Now the t-star, the t critical value, will be slightly different because if we just used a z-score here, we would get an interval that wasn't as accurate as our confidence level says it is. So this is in the case of knowing our standard deviation. So we would have our sample mean, x bar, plus or minus our critical value times our standard error. And then remember this whole thing, the critical value times the standard error is called our margin of error. So that's gives you the above and below the point estimate. And you find the critical value of z star the same way that we have been before. So choosing your sample size, we did this a little in the 8.2 packet where we looked at choosing a sample size that's appropriate. So we would find a critical value of z by determining our margin of error. Let's say we wanted to be off by only 0.05, then we would substitute 0.05 in here for margin of error, and we would put in the appropriate the critical value, z star, for whatever confidence level we have. So if it's 95%, remember we use 1.96 times our standard deviation, and that would have to be less than or equal to our margin of error. So that's how we would determine a sample size. Like let's say if we wanted to have our confidence interval be between, we would use 0.05 for margin of error, if we wanted our interval to be 0.1 or 10% in length for a proportion. So in this case, if we used 5 for our margin of error, like let's say we wanted to estimate the amount of diseased animals in a certain habitat, if we wanted the margin of error to be 5, then that means we would get plus or minus 5, so an interval of 10 that would hopefully capture the population mean. So again, that's just solving for n. Z star is based on the confidence level. Margin of error will be given to you. And then this one will require you to know the population standard deviation. In reality, we oftentimes don't know that. So what we have to use, and we'll be mainly using for population means, is what we call a t-distribution, which is similar to a z-distribution but a little bit different and more accurate. So the t-distribution is when the population standard deviation is unknown. So in order to find the correct t statistic to use, we have this in the back of our book, and you'll be given these when you take a quiz or a test. In order to choose the correct t statistic, you have to look at degrees of freedom. So degrees of freedom are based on sample size. So all you have to do to find degrees of freedom is subtract 1 from the sample size. Nice and simple. That's down here. So if I take the sample size and I subtract 1, then I'll get the degrees of freedom, and I'll know which t statistic to use in our table. So the main difference in the t statistic is that the standard deviation here is the standard deviation of the sample mean, x bar. It's not the standard deviation of the population. So we'd have our x bar minus mu over the standard deviation, our estimate of the standard deviation for the population. Now the reason why we use t statistic instead of a z-score is because the z-score doesn't hold up when we don't know the population standard deviation. So the main thing you have to know is if you don't know the population standard deviation, t statistic. So to construct your confidence interval, we take our sample mean, x bar, as our point estimate, and then we find the standard deviation of the sample, and then divide by the square root of n. This tells us how far x bar will be from our parameter on average in repeated simple random samples of the same size n. So that would give us the standard error of our sample mean. So we'd have our statistic, which is our sample mean, that's x bar, plus or minus the critical value, which is based on our confidence level, our t statistic. So here we represent that as t star, times the standard deviation of the statistic, so standard deviation over the square root of n. So t star is the critical value given to you in the table, and you figure it out by subtracting 1 from the sample size. So we can use this interval when the population distribution is normal or the sample size is large, so greater than or equal to 30. Remember this? What theorem is that? Central limit theorem, greater than or equal to 30. So if the population distribution is normal or the sample size is large, so being bigger than 30, and then the population is at least 10 times as large as the sample, so the 10% condition. So it has to be random. We need to have an SRS to have an unbiased estimator. It has to be normal. However, for population means, this is the condition that's different, the normal condition. Because it's not a proportion, whereas before it was n the sample size times the proportion, p hat, has to be greater than or equal to 10, or n times the quantity 1 minus p hat has to be greater than or equal to 10. Both of those things had to be satisfied. Now we don't have a proportion, so we just have to make sure n is greater than or equal to 30. If it's not greater than or equal to 30, we'll talk about what to do in that case in just a second. And then independent, meaning we can't sample more than 10% of our population. Those of you who are in block 6 and we did the bead activity, you saw that our point estimate didn't hold up when we violated this condition. So what do we do if our sample size is not 30, but let's say it's 20? That's what we call a robust procedure. That's what we need our procedures to be robust. So a procedure is robust if it holds up and stays accurate when a condition for using the procedure is violated. So when a condition like the normal condition is violated, like let's say we had a sample size of 20 as mentioned before, but our conditions maybe still be able to hold up, we call that a robust procedure. So in the case of a t statistic, if we have a sample size less than 15, we can use the t procedures if the data appear close to normal. So roughly symmetric with a single peak and no outliers. So if there's clear skew or there's outliers present, we can't use t. So if it's less than 15, but it appears close to normal, so we'd call that approximately normal, meaning it's roughly symmetric, single peak, no outliers, we can do it. If a sample size is at least 15, the t procedures can be used, except when we have outliers or a strong skewness. If it's slightly skewed, that's okay. But if it's at least 15, we can use them, except if we have outliers that are way off or strong skewness, because they'll throw off our normal, our approximately normal sampling distribution. We try to approximate it. And large samples, you can use the t procedures for even clearly skewed distributions when the sample is large and is greater than or equal to 30. So once we're above 30, we don't have to worry about it at all. Less than 15, it has to look approximately normal. At least 15 to 30, if it's slightly skewed, that's fine, but no outliers or no strong skewness. So go over the lesson in your book, read the examples, 8.3, and read through the lesson, especially the summary. Here's the multiple choice. How many degrees of freedom can you use for a t statistic in terms of the sample size n? So here are your 4 options. So how many degrees of freedom? This will help us figure out what part of our table to use. We'll go into looking at the table in next class and how to calculate it. This will help us figure out what to use. So how many degrees of freedom? The same as the sample size, n plus 1, n minus 1, 1.96 times n, or 2.576 times n. So go through, read through the lesson, and then answer this one and the conceptual question below.